Hello, everyone. This is the lecture for section 6.3, Taylor and Maclaurin series. So we've learned everything we need to know about series now, right? We know what a power series is. We know how to sort of determine radiuses of convergence and intervals of convergence, right? Taylor series and Maclaurin series. They're a pretty big and profound, very substantial jump in terms of sort of like the utility of mathematics, not only in, just studying more math, but you can really apply it to physics, chemistry. A big thing that I'm going to show you guys in this section is computer science, okay? Big, huge thing that happens with Taylor series, what we can use Taylor series for when we start talking about computations and all that stuff, okay? I already made you do an example of it, but now I'm going to sort of specifically, develop the idea, okay? So the first idea, or the first thing that I need to do is sort of give you guys an overview or the construction of a Taylor or Maclaurin series, okay? So I hope there's no, I looked this over multiple times. I hope there's no typos here, okay? But hopefully you guys follow along. This is the same stuff that's in the textbook. If you guys want to follow along the textbook, that's also fine as well, okay? So let me, second, there we go. I need to fix up my notes. There we go. All right. So let's start. Suppose, right? Pretend we have a Taylor series expansion, or sorry, so pretend we have a power series expansion like this, like such, okay? So f of x is the function, whatever it may want to be, right? That sum, this one, is the power series expansion, and this is just me writing the whole power series out, okay? Suppose we have that, okay? And all of this, just keep this in mind, right? This is the thing that's floating in the back of our minds, that it's centered at a value x equal a, okay? Okay, so suppose we want to evaluate f of a. So, whatever the function is, right? And we want to plug in the value a into our function, right? That is equivalent to plugging in a into our power series, right? Okay. Which implies that we plug in a into our sort of expanded, completely big, huge expanded power series all the way out to infinity, right? And hopefully you guys see what's going on, right? A minus a, that cancels away, that cancels away, that cancels away, right? So the only thing left is C0, C sub 0. Okay, cool. Suppose now we wanted to find f prime of a, right? So we'd need the first derivative of our function, right? So the derivative of our function, f prime of x, right, should be the derivative of its power series. Boom, right? And if you write this out, it should be this thing right here, okay? And I'm maintaining a fair amount of the subscripts and the exponents there because you'll see it'll be pretty important for us to use, right? So this is finding just the power series of the derivative, right? So if we want to plug in want to plug in x equal a to our function, right, then that is equivalent to plugging it into our derivative, right, which means it's equivalent to plugging it into our power series, right, which means if I write it all out, this is what it's going to be equal to, right, and lo and behold, the same thing happens here, right? So a minus a, that cancels away, a minus a, that cancels away, right? A minus a, that cancels away. The only thing that is left is C1. Okay? Okay. We're going to do it again. Suppose I wanted the second derivative at a function a, right? Suppose I wanted f double prime of a.
BRP? Yes, I'm going to alternate.
Sorry about that. Got a friend staying over. Okay. So if we want the second derivative at a value x equal a, right, then that is, that's the second derivative, right? That is the power series for the second derivative, right? And it is equivalent to this right here, right? Okay. So then again, if I wanted the second derivative at a value x equal a, then that is equivalent to me plugging in a to my second derivative, right? Which is equivalent to plugging in a to the entire power series, which means I'm plugging in a for this whole entire thing right here, right? And again, right, a minus a, that cancels away. A minus a, that cancels away. A minus a, that cancels away, right? So then all we're left with is 2 times C2. Okay. Okay. If I wanted the third derivative at a value x equal a, right, then I've got to do the same thing. F prime, triple prime of x is all of this, right? This is the derivative of my power series, which means this is my expansion of my power series, right? So then if I want the triple prime at a, that means I'd be plugging in my a, right? Which means this is my expression here, and this is supposed to be a here. I told you it was going to happen. I'm going to want an a there, right? Which means my expansion is going to look like this, right? And the same thing happens again, right? A minus a, this whole thing goes away. A minus a, this whole thing goes away, right? So on and so forth. I'm just left with this. Okay, so I want everybody to look at this really quick. I'm going to highlight some pretty important things here. I'm going to do it in green. C0, C1, 2C2, 3 times 2C3. That is all equal to f of a, f single prime, f double prime, f triple prime. Okay, so we can keep going, right? But we can see, hopefully you guys see that. Uh-oh. There we go. Hopefully you guys see that what I've highlighted was each one of those equalities that we ended up finding, right? Okay. This one, the first one, tells us C sub 0 is equal to f of a, right? This one tells us C1 is equal to f prime of a, right? This one tells us C2, let me move this down a little bit, C2 is equal to f double prime of a all over 1 times 2, right? The next one tells us it's going to be C3 is f triple prime, 1 too many, 1, 2, 3 of a divided by 1 times 2 times 3, right? This one, I didn't do this one, but you guys hopefully can see the pattern, right? C of 4 is f1, 2, 3, 4 prime of a, right? And that's supposed to be an a right there. I knew there was going to be a typo in there somewhere. 1 times 2 times 3 times 4. Okay, now I'm going to add in a little bit back over here to the first one. This is equivalent to 0 factorial, 1 factorial. Okay, this one, f double prime at a, 1 times 2, that's 2 factorial. f1, 2, 3, a, this is 3 factorial. This one, right, it's going to be f1, 2, 3, 4 of a, 1 times 2 times 3 times 4, that is 4 factorial. So we've got this formula going on now. And hopefully you guys see where this is going to, right? Our CNs are equal to the nth derivative, whatever derivative we're looking for, right? We're looking for the nth derivative divided by that number derivative factorial, okay? this gives us coefficients for our power series, right? And this right here is the construction of the Taylor series and Maclaurin series, okay, which is summarized in the definition below, okay? So suppose, right, that you have a function, f of x, right, and it has all the derivatives, right, at x equal a, then the Taylor series for that function at x equal a is this right here. So it is no longer, if you guys sort of take a look, right, all of this used to be our c sub n, right, times x minus a to the n. A Taylor series is when that is when our c of n is defined to be those terms right there. So now we actually have specified specific things, right, for our coefficients up front, okay? And if you want to expand a Taylor series out, that's this right here, okay? A Taylor series that is centered at 0 is what we call a Maclaurin series. So a Maclaurin series basically is a example, a subset of Taylor series, okay? A Maclaurin series is always going to be centered at 0. Taylor series can be centered anywhere, where this a value right here, right? If you remember, right, when we want a power series centered at a, that a is going to be that x minus a bit, right? Okay? Okay. A theorem. This follows from the uniqueness of a power series. So if you guys remember from the previous section, we had something that dictated the uniqueness of a power series, right? So if you had a function and you found two power series, right, for the same function, then what you essentially found was two different versions of the exact same one. So somehow we were able to grab one Taylor series and turn it into the other, right? Okay. All right. So now, let me do an example, okay? This one right here. Okay, so what I'm going to do is I'm going to find the Taylor series for this e to the 2x centered at 0. And I'm going to find its radius and interval of convergence, okay? And I'm going to do the ends, right, just so that we have them sort of written out, okay? I'm going to find them out, and I'm going to sort of write them out as a Taylor series at the end, okay? So when n is equal to 0, right, that's going to be n f of 0 to the x. So then this should be the original. So it's just going to be, whoops. This is supposed to be just e to the 2x, right? The first derivative of this is a chain rule, right? So it's going to be 2e to the 2x. The next one is going to be 4e to the 2x. When we want n equal to 3, right, that's going to be 8e to the 2x, right? 16e to the 2x, 32e to the 2x. So hopefully you guys see the pattern that's going down here. The nth derivative, right, is going to be some 2 to the n e to the 2x, right? Okay, so we found our derivatives. Now I want to go ahead and find the coefficients. So these are supposed to be our c sub n's, right? And for this, we just need to plug in our value 0, right, into each one of these derivatives, do the n factorial over it, we're good to go, okay? So then this is going to be e to the 2 times 0 over 0 factorial, something that probably hasn't been shown to you guys. 0 factorial is 1. Okay. Next one, 2e to the 2 times 0 over 1 factorial, right? 2 times 1 over 1 factorial, 2. Next one, 4e, 4e to the 2 times 0 over 2 factorial, 4 over 2 factorial. This is going to be 2. Okay, it happens sometimes, right? 8e to the 2 times 0 over 3 factorial. So it's going to be 8 times 1 over 3 factorial, 8 over 6. Okay, 4. This is going to be 16e to 0 over 4 factorial. Now, you don't really need 16 times, whoops, whoa. 16 times 1 over 4 factorial. This is going to be 16 over 24, right? I'm not going to entirely do this last one, but it's going to be 32e to the 2 times 0 over 5 factorial. And if you do this right, 32 over 5 factorial, okay? Right? So what you guys hopefully see, right? And I'm going to highlight the numbers that sort of are important, or the fractions that are going to be important. Right, and sort of ancillary importance are these right here, if you actually want to work out the factorial, right? But hopefully you guys see that the coefficient up front, right, is going to be some power of 2 to the n, right? Some power of 2 divided by that power of 2 factorial. So it's going to be 2 to the n, right? E to the 2 times 0 all over n factorial, right? E to the 2 to the 2 times 0, that's going to be 1. So this is going to be 2 to the n over n factorial. So this means that my f of x, right, is equal to e to the 2x. It is also equal to the sum. Let me write this out right. Whoa. It is also equal to the sum n equal 0 to infinity, right, of 2 to the n over n factorial, right, times x minus 0 to the n, since we wanted it centered at 0, right? So if you guys just take a look at this, right? Let me actually do it in red. This is my f n prime of a over n factorial, right? Times x minus a to the n, right? So this is all now equal. I'm just going to clean it up just a little. I'm just really going to get rid of that 0. So it's going to be sum n equals 0 to infinity, right, of 2 to the n over n factorial times x to the n. So this right here, and I'm going to highlight it in yellow, that is our Taylor series expansion for e to the 2x. So what's left to do, just so that we can just double check, right? We're going to do the same test that we did before, where we're going to go ahead and grab our Taylor series expansion, right? Plug it in right next to our function, and hopefully, right, if we did everything right, they should start to match up, right? So what I'm going to do is this. I'm going to say f of x is equal to e to the 2x, right? I'm going to make my, there we go. Okay, and then I'm going to plug in my Taylor series expansion, just how you see it, just how we did before. So I'm going to do the summation, n equals 0 to infinity. Well, I'm going to do k, right? 2 to the n divided by n factorial times x to the n. And I'm going to add my slider. I'm going to make it go from 0 to 100. I'm going to do the steps by 1, right? So if we did this right, this red line, which is my Taylor series expansion, should start getting closer to this black line, right? Which is my e to the 2x, right? So let's go ahead and hit play and look at that. It is matching up pretty nicely, right? It oscillates, of course, right? And that's fine. There's no big deal with that. But it's matching up. And that's what is more important, right? And if you take a look, let me zoom out. It looks like it's matching up really far out. Like if I let this, like I made it stop at 100, right? But if I made it go to 1,000, it looks like it would continue to crawl over in the negatives, right? And then same thing in the positives. It's like sort of laying on top of it, right? So it looks like our radius of convergence should be all real numbers. So let me go ahead and pause it, and let's go back into our notes, right? Almost there. There we go. So now let's find our radius of convergence. Okay, so our radius of convergence, we're going to do it the same way that we did in the previous section, right? We're going to do this by by ratio test, right? So limit as n goes to infinity, right? We want the absolute value of an plus 1 over an, right? And that is equal to the limit as n goes to infinity, all of this, right? So it's going to be 2n plus 1 over n plus 1 factorial times x to the n plus 1 divided by 2 to the n over n factorial x to the n, all in, right? This is equal to the limit as n goes to infinity. If you do it right, this is going to be equivalent to 2 over n plus 1 times x, all in absolute value. And in order for this to converge, right, according to ratio test, this has got to be less than 1, right? Okay. Now, we're going to be talking specifically about this thing right here, okay? Limit as n goes to infinity of 2 over n plus 1 x, right? We need this to be less than 1, right? Now notice what happens, right? X can be any value, right? The n plus 1 that's on the bottom, right? As n goes to infinity, this thing goes to 0. This whole thing goes to 0, right? So then that means that the limit, right, as n goes to infinity, right, of 2 over n plus 1 times x, and that's supposed to be absolute value, right, is going to be equal to 0, which is always less than 1, right? So I'm going to summarize that in the phrase down here, right? For any x value, right, as n goes to infinity, right, the limit also tends to 0. So when you see this happen, right, hopefully this is the telltale sign. My radius of convergence, right, is equal to infinite, right? So then my interval of convergence is negative infinity to infinity. And we are done. So we found our Taylor series expansion. Okay. And then we found that the interval of convergence for this Taylor series expansion is from negative infinity to infinity. Okay. Woo! That's a lot of good work there. Okay. What comes up next is quick checks. So I want you guys to try the same exact process that I did up above. Find all the derivatives, right? And I want it centered at 0, right? So find the Taylor series expansion, right? And determine the radius and interval of convergence, okay? And it turns out, okay, the two Taylor series that you find in your quick checks, right? They are the most profound ones. It's three big ones that really are super, super, super important in the study of in higher level maths once you get there, right? It's the Taylor series expansion for sine of x, the Taylor series expansion for cosine of x, and then the third more important one is the Taylor series expansion of e to the x, which is this one. Okay. If you do the same thing that we did up above with the example that I gave you, right? This one should pop out just as easy. Okay. Cool. Now we have to study what we're going to study is the bit that's going toward the computer science portion that I was alluding to for so long. Okay. So suppose you truncate a Taylor series at the kth term. Suppose that because all of these, right, any Taylor series expansion goes off to infinity, right? So suppose you slice it somewhere. You say, I just don't want to do it anything past, I don't know, x to the 10th or x to the 25th, okay? What you do there is you get this thing called the kth Taylor polynomial for a function, okay? So I have to preface with something, at least for this definition and for this section that's coming up, right? The textbook, I believe, has bad form when it does this. So I'm correcting a little bit of the notation from the textbook, but the idea is still there, okay? When you want to define the kth Taylor polynomial, right? The thing that I really am switching out is the k value, okay? Since n is used as a counter, right, as the index, you don't want to use it for two things. So, good mathematical practice is to define it using another number. The textbook did not. I am. That's the only difference, okay? The kth Taylor polynomial, right, is written this way, p, little p, sub k of x, right? And it's essentially the sum, right, up to a value k. So it's just Taylor series expansion up to a value k, and then you stop at k, right? So that's what I mean by here. See how I stopped it at a value k? Okay, it doesn't keep going. There's nothing over here, right? There's nothing over there. It just stops at k. Okay. And again, if it's centered at 0, right, then it's known as the Maclaurin polynomial. That's the only difference. Okay. That's it. Okay, so there's an important thing behind the kth Taylor polynomial and the kth Maclaurin polynomial, and that is that has to deal with the remainder theorem for Taylor's expansions. Okay, so the first thing I'm going to do is I'm going to define what's called the remainder function. Okay, that remainder function is this. Okay. And that is equal to the function itself minus the Taylor series expansion for it. Okay. Then for each x in the interval I, where I is the interval of convergence, right, there's got to be a c where the remainder function, right, is equal to this right here. Okay. And if that function, if this part right here, right, is bounded by some value m, right, then my remainder function has got to be less than this thing, okay? This is, I mean, if you want to look at the specifics for all of this, it's all in the textbook. This is just basically studying the remainder, defining it, and then sort of bounding the remainder from above to a specific value. And it is used in conjunction with the thing from below. It is used with the second theorem that's down here, the convergence of a Taylor series, right? That suppose that you have a function, right, and its Taylor series is this, right, converges to f of x, right? It converges to your function if and only if the remainder at that value x is equal to 0. So essentially, right, just keep this in mind, right? Your remainder function is equal to the original minus the Taylor series polynomial, right, to a value k. Okay, that remainder, right, if it goes to 0, right, then your Taylor series converges to your function. This is essentially just saying that your remainder, right, the difference between your function and your Taylor series polynomial, right, the difference between those values are going to 0. Okay, and this essentially is these two theorems in particular put together, right, give us the strong, heavy-hitting conclusion to basically Taylor series as a whole that says, right, that if you have a function and it has all its derivatives, okay, then you can approximate any function you want, right, using a Taylor series polynomial. If you have any function and it has all its derivatives, then you can approximate your function using a Taylor series polynomial, which is very profound, okay? These two theorems together give us that, okay? Now, why is it so important for us to do these things, okay? The two theorems above give us that the Taylor series expansions, right, are very good approximations, right, to certain functions, right? Hopefully you guys, maybe you guys have probably thought of this question, right? So whenever I type in, e to the second power, right, or ln of 0.5, how does the calculator know that stuff? And quite frankly, the answer to that is the calculator doesn't. It does not know what these values are. It does not. So hopefully you're asking yourself, right, or you've asked yourself before, how does the calculator know what the hell it's calculating? Right? The answer to all of those questions is it doesn't. Okay? So there's a bunch of stuff that we don't like that we know it means something, right? But the calculator doesn't. Specifically, right? The calculator doesn't know what ln means. It doesn't know what cosine of x means. It doesn't know what sine of x means. We know what it means because we've studied math for so long, right? We know that the ln is giving us back the exponent when we do e to some power and we want it to be equal to x, right? When we say cosine, right, we know that that means that we're going out a radius, right? And we're going up an amount, right? How far left or right do we have to go, right? If we want to go out a specific radius to a given angle, right? And then same thing for sine, right? If we go out a specific radius at a given angle, how far up or down did I have to go? That's what sine and cosine are, right? So we know what those things mean, right? But our calculators don't. They don't know what those things mean. So how does a calculator figure it out? Okay. Now, this is something that you'll learn if you do computer science, right? The only thing a calculator can do, right, really, is add, subtract, multiply, and divide two numbers. That is all it can do. So how does a calculator know how to find sine of pi, cosine of 0, ln of 0.5, right? And the way it does it is it uses Taylor series expansions to find the approximations to much more complex values like these, okay? Because if you take a look at it, right, I can grab between the two theorems from above, I can grab any function that I want, right? And get a pretty good approximation to my function using a Taylor series polynomial, where I can just sort of go out a couple terms, right? And then chop it off from there. And I can just say, this is close enough. Okay. And if I do that, if you take a look right at the result, right, we have polynomials, right? That is the result, end result of all of this. We have a polynomial, right? Which is, if you take a look at the polynomial in and of itself, right, if I wanted to compute anything from that thing, right, all I need is addition, subtraction, multiplication, and division, which is something that a calculator can do. Okay. This in and of itself, the Taylor series expansion, right, is this has been the standard practice for the construction of the software for any scientific calculator that you can think of since the 1970s. This is how we can get calculators to solve these particular sort of oddball values. Okay, so to show you guys what I mean, that's the example that we have down here, okay? So I want to estimate e squared. Okay, and I'm going to do so using a Taylor series polynomial, right? So the question here, the example that I'm going to ask you guys is, what is the least degree polynomial that assures my error is less than 0.0005? And I'm going to provide an expression for the approximation from the Taylor series polynomial. Okay, so the first thing I'm going to do, right, I'm going to note over here, right, that e to the 2x, we found this Taylor series polynomial to be the sum n equals 0 to infinity of 2 to the n over n factorial x to the n, right? So if I want e squared, right, that's going to be e to the 2 times 1. So my x value right here is going to be 1. Okay, so now I'm going to now go back to Desmos, and please use Desmos. Please, please, please use Desmos. It'll make the computations that much faster for you to do, okay? Now, my f of x is going to be the same for all of these, right? What I'm going to do here is, if you take a look, right, this summation that you guys have been plugging in, hopefully you guys have been plugging into your computers, into your tablets, into your phones, right? This right here is your p of x. This is your pk of x, right? Now, I don't want to put the k because it messes up. Desmos can't handle it. So I'm just going to put p of x here, right? And now what I'm going to do is I'm going to make the remainder, okay? Now, I'm going to make this super, super tiny. I'm going to add in a table. And this is what I want you guys to do as well when you do your second quick check that's about to come up. I'm going to make the x that my f of x is going to be the second column. My piece of x is going to be my next column over, right? And then my r of x is going to be my last column. And I'm not going to write in r of x. I'm actually going to say f of x minus my piece of x. So I'm grabbing my f of x, my function, minus that partial, minus that Taylor series polynomial, right? So I want my x to be 1, right, because of this right here. So now what I'm going to do is I'm going to fill in this table. And I'm going to keep a track of all the k's that I do. Okay, so what do I mean by that? Right now, let me actually bring it down to 0. I'm gonna actually make this a little, there we go. So I'm gonna start off with k equals 0. So this is gonna be k equal 0, right? My f of x is gonna be 7.3890, right? 7.3890, right? And this is gonna be the case for all of these, okay? My p of k, that is 1. My r of k, 6.3890. So this is still far off. If you take a look at the difference between these two, right? It's a ways away. It's 6.38 difference, right? But now I'm going to start grabbing this k, and I'm going to start increasing it by 1, by 2, right? So I'm going to do by 2, right? So when k is equal to 2, when k is equal to 2, my f of x is still the same. That didn't change, right? My p of x, that's 5, and my r of k is 2.3890. So now the difference between these two functions, right? The difference between this number and this number, right? It's getting smaller, right? Let's go to, let's do a jump. Let's go to 4, yeah? 3, 4. So now I'm at the f of x is still the same. My p of k is 7. So now my difference is 0.3890. I'm taking it from this last column right here. Got it? So if you take a look, right, look at what's happening. My remainder function between the function and the Taylor series polynomial at 4, right, has gotten smaller. I'm going to do it again. I'm going to take this to 6. Let's go to 6. My p of x, my pk of x, right, 7.3555. The difference between the two is 0.0335. Whoops, whoa. 0.0335. You guys hopefully see it's gotten smaller, right? Let's go to 8. 8. My f of x still the same, but now it's 7.3873.00175.4. So now the difference between f of x and my Taylor series polynomial, right, is only off by this much, 0.00175.4. Now, we need it down to 0005, right? 0005, 0.005. So we're almost there. And let's go ahead, since we're getting closer now, let's go ahead and do 9. My p of x is 7.3887, and the difference is, let me do it over here, 3.4357, and this is times 10 to the negative 4th. Hopefully you guys remember how this works. I do 1, 2, 3, 4. My decimal's there, 1, 2, 3. So this difference is 0.0034357. This is our magic number right here. Right? This now means that the error between my function and my Taylor series polynomial, right, is less than 0.0005. This is as far as I needed to go. So that means our approximation is this right here. This right here is a decent approximation, right, to e squared. Okay, now You guys are probably like, oh, that's cool. All right. Not bad, not bad. But so what? So what? Right? We have the Taylor series expansion, right? Our Taylor series expansion is this right here, right? So according to what we just did, we just have to go out to the 9th Taylor series polynomial, right? Plug in 1 to everything, right? And that is an approximation to e squared using our Taylor series polynomial. So let me show you guys what I'm talking about. So I'm going to write it down here. P9 of x, right? I'm going to write it out. 1. Let me make sure 2, 0. Yeah. 1 plus 2 over 1 factorial times x, right? Plus 2 factorial, 2 squared. This is going to be a little tight. 2 squared over 2 factorial, right? X squared. Plus 2 to the 3rd over 3 factorial, x cubed. Plus 2 to the 4th over 4 factorial, x to the 4th. Plus 2 to the 5th over 5 factorial, x to the 5th. Plus 2 to the 6th over 6 factorial, x to the 6th. Plus 2 to the 7th over 7 factorial, x to the 7th. This is long. Plus 2 to the 8th over 8 factorial, x to the 8th, plus 2 to the 9th over 9 factorial, x to the 9th. This right here is the Taylor series polynomial for k equal 9. All right? Now, remember how I said up here, right, that we plugged in 1. Right? So if we plugged in 1 for x into this polynomial, right, we get this, right? We get, so p to the 9, right? We get 1 plus 2, 1 factorial plus 2 squared, that is 4 over 2 factorial plus 8 over 3 factorial plus 16 over 4 factorial plus 32 over 5 factorial plus 64 over 6 factorial plus 128 over 7 factorial plus 256 over 8 factorial plus 512 over 9 factorial. This right here, let me actually do it in green. This is pretty profound. I want you guys to see what this is, right? This right here is the 9th Taylor polynomial, right? For my function e to the 2x, evaluated at 1. This right here, right, is an approximation. This right here is an approximation to e squared. And this approximation now is off by just 0.0003. It is off by this much. It is off by only that much. So that's why this is so profound. Remember how I said, right? A calculator can add, subtract, multiply, divide. It doesn't know how to take exponentials. It doesn't know e to the some odd power, right? Does that make sense? It doesn't know that stuff. It doesn't know it at all, right? But this P9 evaluated at 1, this thing in the green, right? That is an approximation to the value that I need, and it only needs additions, subtractions, multiplications, and divisions. In the case that we have here, right, it only needs additions, multiplications, and divisions, which is something that a calculator can easily do, and it can do it very quickly. Okay, this is the big part behind computer science. So this is saying that every single calculator, right, anything that has sine of x, cosine of x, tangent of x, anything that has e to the x, right, or ln of x, it doesn't know what it's doing really. It's actually grabbing a Taylor series polynomial that's been loaded into it, right? It's grabbing that Taylor series polynomial and evaluating it at a particular point that you are wanting. That's it. So the calculator has no idea that you're trying to find e to the second power. It is just computing something out based off of its Taylor series polynomial. That's it. That is the importance behind the Taylor series. This used to be done by hand. This used to be done by hand. If you guys remember watching that movie Hidden Figures, this is what people who were called calculators back then, this is what they computed. This right here is what they computed. Now it's done by calculator. And it does it by Taylor series expansions. Okay. So what I want you guys to do now is I'm going to continue on with the same examples for the evens and for the odds, right? So the evens found the Taylor series expansion for sine, and the odds found the Taylor series expansion for cosine, right? I want you guys to go find sine and cosine of 1 and give me the same table that I did up above, right? Give me the least degree polynomial that assures me an error less than half of a, what is that, half of a 10,000th? Okay. Do the same table, do the same process, right? And then provide me the approximation itself. So provide me, like I did here, right? The approximation using the Taylor series expansion. Okay. All right. And I believe that is it. The next thing that comes up is lecture questions. So if you guys have any questions on how to do these, please drop me a line. Either stop by my office hours, stop by the math lab if you need it, or simply just drop me a line. Okay. Besides that, I think I'm done with this section. Happy studying.